Also, guys, I just want to sort of look at this chapter, or sort of where we are on test. So far we've really just had these first two on test one. On this next test, I expect that we'll have these two. Chapters 3 and 4 are really big chapters, and that might be all that we get. Excuse me. Thank you. We might get a little bit of chapter 5, just with dot product, just definition of work and seeing dot products and what have you. We might get a little bit on exam 2, and then we'll have two more exams. We'll get these, probably these three: energy, momentum, and collisions and rotational motion on exam 3. And then that would just leave us with these last two topics for exam 4. Uh, Elasticity and equilibrium is really just a rehash of stuff that we've done before. It's sort of a precursor to your statics class that some of your pre-engineering students will take. And I often do that as a take-home test, or a portion of it as a take-home test. And then we'll do vibrations and waves. I might nix that and instead do optics, or I might do optics in addition to that. You geomatic students, that's like the one topic that you really have to cover, and that's the one topic that we got rid of last year. So Dr. Balaji got on to me about that, so took me to the woodshed, as they say. But anyway, so we're going to cover optics at the end of this semester, and we may or may not get to vibrations and waves. Okay, so just give you a little orientation about where we are. A couple of years ago, we trimmed down a lot of content in this course, but the state did, uh, statewide. So normally, if you were taking physics at LSU or UL, you would take 3 semesters of physics to get the full sequence. Engineering majors, most engineering majors still only need to take 2 semesters, and that's the way you do it at LSU too, by the way. But anyway, if you care, that's sort of where we stand. Let's work through, and of course you care, right? You care? Not really. Okay. Well, let's work through this problem. Uh, this was from an old test, and then we'll work through those 3 problems that I handed out. Were there any extras? These are extras. Thank you, Lazarus. Okay, so in this figure, a stone is projected, it's shot at a cliff of height h with an initial speed of 30 meters per second at 50 degrees above the horizontal. It strikes at A, the point A, 2 seconds after launching. I want you to find the following. Thomas? Thomas, here you go. All right. I want you to find the following: the height of the cliff, the speed of the stone just before impact at A, and the maximum height above the ground. See, I think there was a mistake with this problem. Why don't you see if you can find it? Go ahead and get a start on this. I will help you in just a second. While you're starting on that, I'll be right back. I have to pick up something. Fairly straightforward problem here because we have the time. It makes it pretty easy to solve this. You can treat each of the 3 parts sort of independently. Remember that with our kinematics, we have our kinematics equations still hold. That's y equals v naught y times t. It's 1/2 ayt squared. And we have vy equals v naught y plus at. And then for our x component, we really just have x equals vx times t, where vx is equal to our initial velocity in the x direction. What will be the first step on this problem? Right. You want to break into your x and y, which means you'll want to find what? Right, you want to find the x and y components. That's almost always going to be the case that you'll want to find your x and y components. So I'm just going to go ahead and do that up here. V naught x and V naught y. That's going to be V naught. Gosh, what is the x component again for the cosine of theta, right? So it's going to be cosine of theta. That's V naught was 30 times cosine of 50. And then similarly, this is going to be 30 sine of 50. Anybody have those values? 22.0. So 23 then. All right, 23. So those are our V naught x and our V naught y. And now if I want to find the height of the cliff, I just say I know my y function is V naught y times t plus 1/2 ay t squared. V naught y is 23. What time do I use here at point A? What is the time elapsed? It's going to be 2 seconds. That's in the problem. Minus 5, that's just the 1/2 of negative 10 times 2 squared. And I get my y position as 46 minus 20. So that's equal to 26 meters. So it tells me that this distance from here down to the ground is 26 meters. All right. I also want to know what is the speed of the stone just before impact. So I know that my stone has two components of velocity. It has the x component of the velocity, which we already know, right? That's going to be the, there you go. It's going to be the, what we've already found, that 19.3. So my Vx is 19.3 meters per second. And then I also want to find my Vy. Now remember the Vy changes. Initially, it's big and in the positive direction, and then it gets smaller, and then it's 0, and then it begins increasing in the negative direction until it returns to the original value down here if it were to reach that point, where it's going to have the same magnitude as it did initially. Go with me on this? Yeah, sort of, kind of? All right. So I can find that Vy. It's just going to be V naught y plus ay times t. V naught y is up here. It's 23 minus 10 times 2. That's 3 meters per second. All right. Can you look at that and tell me what's wrong with this figure then? It should be negative, right? That my velocity in the y direction at this point is actually negative. So where in the trajectory then does this object strike the cliff? It's on the other side, right? So this time was a little short. Some time greater than 2 seconds has elapsed when it's over here. So a better way to draw this figure actually would be to draw the cliff right here, that it strikes the cliff somewhere right here. Y'all follow me on why that is? Because the velocity in the y direction is positive, and the velocity in the y direction is only positive to the left of this, to the left of the, I don't know what you call it, the apex or whatever, the maximum height. Okay, so that's my, now I can find my velocity at that point. It's just going to be the square root of these two components, 19.3 squared plus 3 squared. That's going to be approximately equal to 20 probably, right? If I have that. About 20. Yeah. 19.15. I'll just call it 20. meters per second. So that's my velocity at that point at t equal 2 seconds. And then the third part asks you what is the maximum height above the ground. Now, it's going to have to actually, in order to solve this, if this is my trajectory, I know that t equal 2 seconds occurs right about here, so I need to find out what is this time. Now, it says that it stops, but we'll go ahead and ask the question, well, what if it actually proceeded past that point? And so we'd have to go through the same procedure that we've done before on other problems, where I find what is the time at the top. And so I would say that v top is equal to 0, and that's equal to v naught y plus ayt. So I'd say 0 is equal to 23 minus 10 times t. Pardon me, it should be 23. So t is equal to 2.3 seconds, which goes back to that original idea that if this is at t equal 2 seconds, then this time has to be bigger than that. So this is at 2.3 seconds. And to find the maximum height, I would just say y is equal to v naught y times t plus 1 half ayt squared. That is 23 times 2.3 minus 5, 2.3 squared. Here again, I've just taken this 1 half of negative 10 and have negative 5. All right. I think that one's a pretty straightforward problem. You could see a problem that's of that difficulty on the exam, or you could have one that's a little bit different. Every projectile motion problem can be different, just depending upon sort of the scenario that's presented, the information that you have, and the information that you're looking for. So I brought some additional problems. Now for your own practice on your own time, you can look at those old exams, and then the homework has a couple of different projectile motion problems for you to work through. But I brought these for us to work in class. Everybody has a copy? James, you hand it back. All right, um, I want y'all to go ahead and start on, so we're not going to do the first one first. We're going to do number 27 first. That's the ball thrown horizontally from the top of a 60-meter building. What I want you to do is just to go ahead and, what I want you to do, I want you to go ahead and draw a picture of what's happening, and then just label everything that you know about what's going on in that problem. And I'll give you a couple minutes to go ahead and do that. So I want you to just draw a picture of what's happening, and then write down everything that you know about what's going on in the problem, and then also write down what you need to know. So just take a couple minutes to do that. Draw a picture of what's happening, write down everything that you know and what you need to know. Okay, so we're looking first at this one. A ball is thrown horizontally from the top of a 60-meter building, and it lands 100 meters from the base of the building. Uh, I have this object that comes off the top. So you should have a picture that looks something like this. It's coming off at a horizontal direction. That makes it a lot easier because my initial velocity only has an x component, no y component. Uh, I also know that this distance is 100 meters. Uh, I know that this distance, the y distance, is 60 meters. And there are a couple of things I want to know. I want to know how long is it in the air. I want to know the initial horizontal component of the velocity. So I want to know what v naught x is. But we also know that that's not just v naught x, but that's also v naught. So I want to know what v naught x is. I want to know the vertical component of the velocity just before it hits the ground. So I want to know vy final. And what is the velocity, both horizontal and vertical components, just before it hits the ground. So I also want to know not just Vy, but I want to know what is V final, uh, the final velocity just before it hits the ground. Some things that I know, just that Y is equal to negative 60, X is equal to 100 meters. Anything else that I know? There are a couple of things that aren't stated. I know my accelerations. I know both of them. I know that AY is negative 10 meters per second squared, and AX is equal to 0. I do also know my initial Y velocity. Thank you. I know that Vy naught is equal to 0 meters per second. All right. Um, Pretty basic problem. I want to use what motion, the X or the Y motion, to determine the time that it's in the air. What's that, Lazarus? Right. I almost always use my Y motion to determine the time that's spent in the air. And by the way, this is a lot like the problem that you did in lab, right, where you're shooting a gun. You know the X and the Y motion, right, the X and Y displacement, so you can find the time. So if you're in lab, this is almost exactly like one of those problems that you did. So let's first just attack A. But you know, sometimes in the problems, you might not find the information in the order that it's asked for. That's okay. You know, just you'll need to approach the problem, and sometimes you might need to know, for example, part B before you can find part A. Don't sweat that. That's just sort of the way that it's laid out. So at part A, I just want to know the time that it's in the air. Um, I'm going to use my Y motion. I know that v naught y is 0, so that makes this really easy to solve. My y is negative 60, negative 5, t squared. So t is going to be 60 over 5. It's going to be the root of 12. The root of 12 is, oh, what is it? Anybody know? What is it? 3.47? 3 point, so 3.5 seconds. All right, so that's my time in the air. How do I find the velocity in the x direction? I know that it takes 3.5 seconds for this object to travel this distance. How do I find the distance in the x direction? Or excuse me, the velocity in the x direction. Right. Lazarus, what did you say? Just said what he said. Right. So we know that our x is equal to v naught x times t. So I can find v naught x is just x over t. So x is 100 meters over 3.5 seconds. That's equal to 29 meters per second. In part C, I'm looking now for the vertical component of the velocity. So I know that that vertical component of the velocity changes with time by this function. I know the time at the end. So this is just going to be my v naught y, which is 0, times negative 10 times t, which is 3.5 seconds, or negative 35 meters per second. So if I go back to my figure up top, if I sketch out the velocity vectors here, when it reaches this point, it has a velocity in the y direction at negative 35 meters per second. I also know the velocity in the x direction. What's the velocity in the x direction at this point? What is it? It's not 100. No, that's the x displacement. That's the x position. But what's my velocity in the x direction at that point? 20 what? 29, right. So that's the same as the velocity in the x direction that we found in the initial horizontal component. So up here, my v naught x was equal to 29. That's also equal to vx at here. And that comes about because the acceleration in the x direction is equal to 0. Have I lost you on this? We feel okay. Yes? Nah? No. Can you tell me? Can I see a thumbs up, a thumb to the side, or a thumb down? Sorta, kinda. Sorta, kinda. Lots of sorta, kindas. All right. I'll step back through it here in just a minute because the next problems are quite a bit more difficult. Um, all right. So here, uh, my d, my vx, because ax is equal to 0, is just equal to 29 meters per second. It's the same as what we found up here. And then finally, part E is asked, what is the velocity of the ball just before it hits the ground? I have these two vectors. One is 29 meters per second. One is negative 35 meters per second. I just want to know what is this resultant vector. If I add the two up, it's going to be the square root of 29 squared plus negative 35 squared, and that's equal to 0. Or excuse me, not 0, I'm sorry. That's equal to 45 meters per second. That's just adding up the vectors, finding the resultant magnitude. Okay, folks, so let me step back through this, okay? Because there are a number of steps here. But again, this is a pretty straightforward problem, so it's a good place to start. And then we'll move on to the next two, which mathematically are a little more difficult. First, we just drew a picture. It's always very good to draw a picture here. This is a pretty simple one. It's coming off at a horizontal direction. You didn't know its velocity, we didn't know its time, we didn't know the final y velocity, and we didn't know the final speed. These were all things that were being asked for. But we do know the x and y displacement. Notice that we made the y displacement negative. The x displacement is positive. We know the accelerations, and we know the velocity in the y direction initially is equal to 0. That's because it's coming off at a horizontal direction. In order to find the time, we consider the y motion right here. So we can solve this equation for t. Because v naught y is 0, that makes this a lot easier. So this is 0, so this whole term goes away. It makes it a lot easier because you don't have to solve the quadratic equation because you only have this t squared term. You don't have a t term. So that makes this pretty easy to solve. And I find the time is 3.5. Next, I want to find what is the initial velocity in the x direction, which is the initial velocity. I know from my range that this is true, that the x is only dependent upon the time, which we now know, and the velocity in the x direction, which doesn't change. And so that gives me the velocity in the x direction, which is 29 meters per second. And then in part C, we want to know the velocity at impact in the y direction. So since I know that v naught y is 0, that goes away. It's all just a times t, negative 10 times my t, which is 3.5 seconds. 3.5 seconds elapsed from when it's shot to when it hits. have to recognize that your Vx doesn't change. So it's the same as what we found in part B. And then in part E, you're just finding the magnitude of those two vectors. All right? Could see a problem like that on the test, something similar. But as I said, projectile motion problems are all different. So you sort of need to go through the procedure, those ideas that, for example, you need to find your x and y components of your initial velocity. To find the time, usually you consider the y motion of the the projectile, uh, knowing that the acceleration in the x and y directions are 0 and -10. And that comes with practice, like knowing how to apply those things. Look at this next one. Is that okay? It's a little more difficult in the way that you solve it, but you still use a lot of the same techniques. Okay, so here we have a soccer player, kicks the ball from a distance of 30 meters towards the goal. Find the initial speed of the ball if it just passes over the goal 2.4 meters above the ground, given the initial direction to be 40 degrees above the horizontal. First, just go ahead and sketch out a picture of what's happening here. Need a picture here. Normally, our projectile motion, sort of the prototypical problem, was something that looked like this. In this one, it starts out similar to that, but it's a little bit different. So sketch out a real picture of what's going on, and then you can write down the things that we know and the things that we want to know. How is the scenario here different from this picture? Uh, Megan, yeah, but something else. Megan, what were you going to say? Right, it goes over the goal. It doesn't actually end right here. In fact, I know that at this point, which is 2.4 meters from the ground, it goes over the goal. So I know that at this point, it's at 2.4 meters above the ground, and this distance is 30 meters. You follow me on this? So this problem's a little bit different because I don't have the full range of motion. I don't know how far it went. All I know is how far it is to the goal, and I know how high above the goal the ball was. I know that the ball was 2.4 meters above the ground at that point, 30 meters. I know something else. Cody, what did you say? You said the right. It does have an initial x and an initial y velocity, which we'll need to consider. And the reason for that is because this angle is 40 degrees. That's really all I know. Of course, I know that, as always, that AY is -10, AX is equal to 0. I don't know what V naught is, but that's what I want to know. I want to know the initial speed of the ball. In fact, that's all I'm really looking for. But I also need to find the time in the course of that. Listen, guys, it's always a good practice, I think, that once you set up the scenario and you know sort of what you know and what you don't know and sort of the physical problem, what's going on in the problem, that you write down those equations. And then you can look at your equations and ask yourself, what do I know and what do I not know in these equations? And then based on that information, you can go ahead and proceed with solving it. So I'm going to write down basically the three equations that we have. That is that x is equal to Vx times t. Y is V naught y times t plus 1/2 AYT squared. And then Vy is equal to V naught y plus AY times t. Further, I can simplify this a little bit, or maybe not simplify it, make it a little more complicated by saying that this is V naught cosine theta times t, right? I just plugged in the x component because I'm looking for this quantity and I know this quantity. I'm looking for V naught and I know what theta is. I can do a similar thing over here. I can say V naught sine of theta. Listen, you should know your components almost knee-jerk now. The x component is cosine, y component is sine. Always remember that. Did I tell you how I remember that? The cosine sine. X comes before y, c comes before s. It's alphabetical, right? X, y, cosine sine. V sine theta t plus 1/2 ayt squared. And then I have this is going to be V naught sine theta plus ayt. Okay, so now I want to mark what I don't know. I'll mark what I don't know in blue. I don't know this, this, or this. I don't know this, this, or this, or this. So that's our problem. I have two unknowns in each equation. I can mark what I do know. I'll mark that in green. I know theta, and I know ay. So I don't know a whole lot. But I have two unknowns, and I have a system of three equations. So I can solve this, right? If I have two equations and two unknowns, I can solve that by substituting one equation into another. Listen, you will very likely have a situation where you have to solve a system of two equations. Uh, if you're not up on that, I'm going to work through this one right now. But if you feel like you need more help with that, just sort of the algebra side, you can come see me. You can also look on Khan Academy. Just Google Khan Academy system of two equations or something like that. And they have a whole bunch of stuff just on basic algebra stuff. But you can come see me and I can help you work through this. Um, when you have a system of two equations, what you want to do is solve one equation for one variable and then plug that in to another equation. It comes sort of with practice. Oh, actually, I didn't list all of my knowns, rather. What are some other things that I know? I didn't, I forgot these over here. I know x and I know y, right? This is my x value, excuse me, this is my y value, and this is my x value. Let's see, I don't know vy. I don't know this value. So actually in this third equation down here, I have three unknowns. So I'm just going to sort of forget about it, because if I look at these two equations, in this system of equations, I have two knowns and two unknowns. I have two unknowns in this system of two equations. Let me write them again down here. I'm sorry, what? No, your 2.4 isn't negative here because we're taking this to be y equals 0. And then over here, it's upwards from that point. So it's y equal positive 2.4. All right. It's only when you're going down is your y displacement negative. That's a good question. All right, guys, so I have this system of equations. Again, these are my unknown quantities, V naught T, V naught T. You want to solve this in this way. You're going to take this equation and solve it for T. So I have T equals X over V naught cosine theta. I know that I solve it for T because I want to leave whatever I'm looking for in that equation. So I know that I'm looking for V naught. So I want to make sure that I don't solve it for V naught. Instead, I solve it for the other variable that I don't know. And then what you're going to do is you're going to take this and you're going to plug it into here and here. When I do that, I I get y equals V naught sine theta x over V naught cosine theta. I just plug that in for t. plus 1 half ay x over v naught cosine theta squared. Listen, if you get to that point, or if you get close to that point on the test, you're going to get almost all the points as far as solving the system of two equations. But you'll almost certainly have a system of two equations that you'll need to solve, either from this chapter or from chapter 4. But you'll need to know how to solve a system of two equations with two unknowns in them. Yes, y'all can do that? Yeah? All right. So I can work this out. Again, reminding myself that I know y, I know theta, I know x, I know ay, I know x, I know theta. I know all those things except for v naught. So this should be a pretty easy thing to solve. I have y equals v naught. Sine theta over cosine theta is the same as tangent of theta. Or if at this point, if you want to put in numbers, I'm okay with that. A lot of students work more easily with numbers, so if you want to do that, that's fine. Although if you put in numbers at this point and you make a calculation error, you're not going to know that you made a calculation error. So it's useful to just be able to work just with the variables here. And very good, the v naughts cancel out. That makes our solution a lot easier in solving this equation. Plus 1 half ay. This is going to be x squared over v naught squared cosine squared theta. That would just be like the cosine of theta squared, right? Um, and then I just solve for v naught. But look, this is a really easy thing to solve for because this is the only v naught that I have in the equation. So I'll have y minus tan theta x equals to 1 half ax x squared over v naught squared cosine squared theta. And then I just want to isolate that v naught squared. I'm going to leave you to do the algebra here, but I'll give you the solution. The v naught squared is equal to, or rather the v naught is the square root of x squared ay cosine squared theta times 2y minus 2x tan theta. There were several steps of algebra that I did. I multiplied both sides by 2, multiplied both sides by 1 over ax, divided both sides by x squared, multiplied both sides by v naught squared, or excuse me, by cosine squared theta, and then took the square root of it, and then flipped the whole thing to give me v naught, because that solves for 1 over v naught, and then I flipped the whole thing. Okay? If you have trouble with that algebra, please come see me, okay? We'll work through that. But I would recommend that you go through these steps on your own. There are several steps there, just to make sure that you can get from this point to this point without any difficulty. Okay? Have I lost you? Sort of, kinda. Sort of, kinda lost. In the algebra, I lost you? Okay, we can step through it. I'll just take a second here to step through the algebra. Uh, I can rewrite this as y minus tan theta x equals to ax x squared over 2 v naught squared cosine squared theta. Then I'm looking for v naught. So I'm going to rearrange these. I'll cross multiply here and here. Ax x squared. You might do this a little bit differently. Everybody sort of does their own algebra. All right, I want to get this back to just v naught squared, so I'm going to divide both sides by y minus tan theta x and 2 and cosine squared theta. that gets rid, I'll do that over here too. I'll divide by that same term, and that gets rid of this, it gets rid of this, and it gets rid of this. And then I just take the square root of this whole thing, and the square root of this, and then that gives me v naught. It looks a little bit different in form, but it's still the same. I have the x squared, this should be ay, not ax. X squared ay, the cosine squared, and then I have the 2y minus 2 tan theta x. All right, so those are sort of the steps of algebra, and then it's really just a matter of putting in the numbers, and when you put in the numbers, you get v naught equals 11. Not too terribly concerned about that you get the number right, but that you get the steps right, I am very concerned about that. That not only can you set it up, but that you can solve that system of two equations. You'll find several examples of systems of two equations in the homework and in the old tests. So I would expect that for the upcoming exam, either for projectile motion or for chapter 4, which we'll get to next week. Okay? All right, let's move on to this next problem. This one's probably the most difficult of the three. Well, it's not that difficult. It just requires the quadratic equation. So I have here a volcano. It ejects hot rocks, hot lava at 25 meters per second at this angle above the horizontal. But then it strikes the side of a volcano at 5 meters lower than its starting point. I want to know the time, and I want to know the velocity of impact. So I have this object. It goes like this, but instead of striking at ground level, it keeps going a little bit. It actually strikes at a distance that is 5 meters below the horizontal. So again, every projectile motion problem is different depending upon the scenario that you have. And in this case, this is how it's different. I know that I'm at 25 meters per second, and I'm at an angle of 23.57 degrees. Just go ahead and get it out of the way to calculate your Vx and your Vy. V naught x, V naught y. I get 23 meters per second. V naught y is 10 meters per second. That's going to be 25 sine of that angle. Okay, so I'll use these. I'm just going to sort of tuck them off to the side. I always like to just do that first because I know I'm going to need those values at some point. So just sort of tuck that off to the side. I can write my three equations. I basically just have three equations. They're really only two, right? But one of them is a variant of them. That is that x equals vx times t, vy equals v naught y plus at, and y is v naught y times t plus 1/2 ay t squared. And I am looking for time and the rock's velocity at impact. So I want to know, first of all, I just need to find the time at this point. I have my time here, I have my time here, and I have it here and here. So those are all unknowns. My known quantities, I'll mark in green. I know what y is. I know what ay is. I know what v naught y is. I know v naught y. I know ay. I do not know vy. I know vx. I do not know x. I don't know this quantity, and I don't know this quantity. So if you were going to solve for the time, which of these three equations would you use, you think? You want to use the y one, right? Because you only have that one unknown in that equation, so you want to solve that for y. Notice it is a quadratic equation, and unfortunately this term does not go away, so that means we're going to have to set it up and use the quadratic equation. So I need to determine what is my quantity y. What is the y displacement at this time? is not just 5, it's minus 5. Right, so remember this is y equals 0. Anything above that point is positive. Anything below it is negative. So y is negative 5. V naught y was 10 t plus 1 half a is negative 5 t squared. Remember the quadratic formula. If I have a function in this form, and I can find t by the quadratic equation, negative b plus or minus the square root of b squared minus 4ac all over 2a. Listen, if you have to use the quadratic, did I tell you I would never have to use the quadratic? I haven't told you all that, right? Okay, that's my one-on-one class. You might have to use the quadratic to solve for a function like this, but if you do have to use it, I will provide the quadratic equation for you. You don't need to memorize it, though many of you probably know it. The way you solve this is you put this equation into this form. So I'm going to write this equation as 5t squared minus 10 minus 10t rather, minus 5 equals 0. And then this is my a variable, this is my b variable, and this is my c variable. It's just the coefficients of the t squared, the t, and then the third term in that quadratic function. I can solve for t now. It's going to be negative 10 plus or minus the square root of 10 squared. I get rid of the negative because it goes away. Minus 4 times 5 times negative 10 divided by 2 times 5. Yes, you're right. Thank you. All right, so that's 10 plus or minus the root of 200, which is 14, divided by 2 times 5, which is 10. So it's either 2.4, which is 24 divided by 10, or negative 0.4. Which of those answers will I take? Huh? Oh, because this is equal to the square root of 100 plus 100, which is the square root of 200. 4 times 5 is 20, times 5 is 100, and these two negatives go away. Which of these answers will I take? I take the positive. Why do I take the positive? All right, negative time, that just doesn't really make any sense. So I take 2.4 seconds. So that's sort of the big answer, is that t is equal to 2.4 seconds. And then part B of this asked the magnitude and direction of the rock's velocity at impact. So I already know part of this. I know that Vx, which doesn't change, is 23 meters per second. Now I need to find Vy. That does change with time. V naught y was 10 minus 10 meters per second squared times t, which is 2.4. So that tells me that my y velocity is negative 14 meters per second squared. Meters per second, rather. I have this thing that comes up. That tells me that here I have a y velocity negative 14. I have an x velocity that's 23. And then if I want to know the resultant vector, v 14 squared plus 23 squared, which is 27 meters per second. So I also want to know the direction. That means I want to know this angle right here. Theta is the inverse tan of the y over the x. That's 14 over 23 is 31 degrees below the plus x-axis. All right, just sort of recap this. Again, I draw a picture of what I have. I like to draw a picture. I think it's probably useful. I sort of orient myself, tell myself what do I know, what do I not know. Here, I did not know the time, and I also did not know the velocity in the y direction or the x displacement. But because I only had one unknown in this equation, which, as I told y'all last time, I would just write, you only have 2 or 3 equations that you need to know. I would just write them out on your form when you get your test and just sort of hold it in front of you. That way you can look at those equations and just sort of ask yourself, what do I know, what do I not know? Um, because this just has one unknown, I can solve it by the quadratic here. I can then get the time. By that time, most of my work has been done. I just need to find the velocity at particular times at that 2.4 seconds, and then do a little vector addition, find the magnitude and direction of that vector. All right? Listen, guys, this next test is going to be the hardest test that you'll face all semester. Okay, so make sure that you're putting in time now. It's going to be a week from Wednesday, 2 weeks from today, right? Isn't that right? 2 weeks from today. So make sure you're putting in time every day on this stuff. If you're lagging behind in your algebra or your trig, right now is the time to be addressing that because it's going to face it to great more difficulty on this test than it was on the first test. And just take a big deep breath. It's okay. It's not really anything new. It's just a little more difficult math on this one. Okay, and don't look so sad because it's gonna be okay. I say it's harder. No, not everybody's gonna fail, but it'll be okay. All right. You have a great day. Okay. Ainsley,